here is the review for exam 3. So let's get going. We'll begin with alternating currents. Now, remember that every word in this review is important because there are going to be many questions on the exam that are conceptual in nature. So please listen to what I say and don't just focus on the math part. When you look at alternating voltages, they are continuously varying. So they are not constant. They are either represented by a sine function or a cosine function. So we could have something like E is equal to E naught cosine omega t. Something like that. And E naught is the peak value, which is the maximum value. And omega is the angular frequency of the voltage. But when you apply an alternating voltage across three components, a resistance, an inductance, and a capacitance, these three behave differently. Number one, when an alternating voltage is applied across an inductor, we see that the voltage leads the current by pi by 2 or 90 degrees. The voltage leads the current. The voltage is ahead of the current by 90 degrees. On the other hand, when you apply an alternating voltage across a capacitor, the voltage lags behind the current. Or in other words, the voltage is behind the current by 90 degrees. That means the phase difference between the voltages in an inductance and a capacitance is actually 180 degrees because one is leading by 90, the other is lagging by 90, so the total is 180 degrees. When you apply an alternating voltage to a resistance, the voltage and current are in phase with each other. P-H-A-S-E. In phase. There is no lead and there is no lag. So that's very important. Now coming to the calculation part, an inductance is represented by L henries. And the inductive reactance, XL, is 2 pi times FL, okay? Inductive reactance, that is X sub L, is 2 pi FL. So there it is, 2 pi F times L. So where F is the frequency in hertz, L should be in henries. So if a problem is given in millihenries, please change to henries. And you can calculate the inductive reactance, and you will get it in ohms. So XL is in ohms, F is in hertz, L is in henries. Now the capacitive reactance XC is 1 by 2 pi FC. 1 by 2 pi FC. Here, C is in farads. So if it's given in microfarads, remember to change it into farads. That's 10 to the negative 6. And again, F is in hertz. But the most important thing to notice is that the inductive reactance is directly proportional to the frequency. That means as the frequency increases, the inductive reactance also increases. On the other hand, the capacitive reactance is inversely proportional to the frequency. What does that mean? That means when the frequency increases, the capacitive reactance decreases. Very important. Totally opposite behavior. So if you have all these three components, inductance, capacitance, and resistance connected in series, then you call it an RLC series circuit. And the total impedance, okay, what is impedance is just, the sum total of the reactances and the resistance. The impedance, represented by the letter Z, which is also in ohms, is given by square root R squared plus XL minus XC whole squared. Okay, so be careful with those calculations. Square root of R squared plus XL minus XC whole squared. And at certain frequencies, XL and XC become equal. If they become equal, then this term becomes 0. That means the impedance is simply equal to the resistance, because square root of R squared is R. Now that is called the minimum impedance. And the frequency at which XL becomes equal to XC is called the resonant frequency. So if you put XL is equal to XC, you will get the formula for resonant frequency. And we'll do that in a minute. But the current is always given by voltage by resistance or reactance. In this case, it's voltage divided by impedance. So if the impedance is minimum, then you know that the current is maximum, because the impedance is in the denominator. So at resonance, number one, XL becomes equal to XC. So the inductive reactance and the capacitive reactance are equal. Number two, at resonance, impedance is a minimum, which will be equal to the value of the resistance. Number three, at resonance, the current becomes a maximum. And to find that maximum current, all you got to do is divide the voltage by the minimum impedance, which is what? The resistance. So there is a lot of conceptual understanding there. Okay, like I said, at resonance, XL becomes equal to XC. And so Z becomes equal to R. Well, because XL is equal to XC. Again, that's the third time I'm saying that. That's so important. And then current is maximum, remember? And that maximum current is the voltage by resistance, because the impedance is equal to the resistance at resonance. Now let's find the resonant frequency. How do you find the resonant frequency? Simply put XL is equal to XC. And we know the formulas for XL and XC. Just put them equal to each other, which is what I'm doing. And then rearrange it mathematically. You will get the formula for frequency. And that is going to be 1 by 2 pi square root LC. 1 pi, 2 pi square root LC. And the reason is, there are two f's here. It'll become f squared, and 2 pi goes down, becomes 1 by 4 pi squared. Just look at that math carefully. So that's the formula for resonant frequency. A very important point here is, does the resonant frequency depend on the resistance? The answer is no. The resonant frequency does not have resistance in the formula. Now, the resonant frequency surely depends on the inductance and the capacitance. So what if the inductance is quadrupled? What happens to the resonant frequency? If the inductance is quadrupled, the resonant frequency decreases to half. Where do I get the half from? Remember, it's a square root 4. Square root of 4 is 2. So the inductance is increased 4 times. That means the denominator is increased 4 times, which means the value decreases to half. So all those kinds of questions you should be able to answer. So that is about the inductive reactance, the capacitive reactance, and the series LCR circuit. This is topic number 1. Topic 2, let's briefly look at a transformer. Remember that a transformer works on the principle of electromagnetic induction. And a transformer can only work on AC. Excuse me. A transformer can only work on AC because you need to have a changing voltage here to get an induced voltage in the secondary because they're not electrically connected. So in a transformer, you have two coils, the primary coil and the secondary coil. The number of turns in the primary is NP. Number of turns in the secondary is NS. And if the number of turns in the secondary is more than the number of turns in the primary, as shown in this diagram, you see the number of turns is bigger, it's a step-up transformer. That means the voltage in the secondary is going to be more than the voltage in the primary. That is a step-up transformer. The opposite one is the step-down transformer. Remember that there will also be currents IP and IS in the primary and the secondary. There are two important formulas that you got to know for a transformer. The ratio of the voltages is equal to the ratio of the number of turns. So if you take Vs by Vp, it should be equal to Ns by Np. Also, the power in the primary is equal to the power in the secondary. That is for an ideal transformer, assuming that no energy is lost. Now, power is current multiplied by voltage. So that gives us IP times Vp is equal to Is times Vs. So got to be very careful there, because if you rearrange this equation, you're going to get Vs by Vp is Ip by Is. You see, it's reverse. See that? The primary and the secondary. So take note of that. So those are the two things that you need for a transformer. Again, remember that a transformer cannot work on DC. Why? Because if you have a constant current here, it's a constant magnetic field. That means no change, which means that there will be no voltage in the secondary. That is topic number 2. Now here is 3. A solenoid. What is a solenoid? It's simply a coil. And this coil could maybe have no core, C-O-R-E. It could just be wound on air, or it could be wound on some other material like iron. Whatever is the case, the inductance of the solenoid is calculated using this formula. Mu naught N squared A by L. Okay, so got to be careful. The caps L is inductance, but the small l is the length of the solenoid, and it should be in meters. N is the number of turns. N is the number of turns. A is the area of cross-section, which is usually circular. Okay, so the A, you see the red shaded part, the area, which is pi r squared. If I give you the radius of that solenoid, you should calculate the area first using pi r squared and then get the inductance. Mu naught. Mu naught is what? 4 pi times 10 to the negative 7. 4 pi times 10 to the negative 7. So plug in all that and you will get the inductance of the solenoid in henries. Okay. Now, topic number 4. You have an oscillator circuit. What is an oscillator circuit? It's simply a capacitor which is precharged connected to an inductor. So there's no resistance in the circuit. We're just assuming that, because usually there is going to be a little resistance. But in an ideal circuit where there is no resistance, what's going to happen is the electrostatic energy of the capacitor will become the magnetic energy of the inductor and then go back and forth. So energy oscillates between electric and magnetic. That's why it's called an oscillator, just similar to mechanical oscillations. And the formula for energy of a capacitor, you see that here, U sub E is 1/2 Q naught squared by C. That's just one of the formulas. And energy of an inductor is 1/2 Li max squared. I max is the maximum current through that. So that's something you have to remember. And the angular frequency, omega, is square root 1 by LC, which will give us back the same formula as before. F would be 1 by 2 pi square root LC. So that's an oscillator circuit where the energy oscillates between electric and magnetic. Number 5. Hope I'm counting correctly. An electromagnetic wave. What is an electromagnetic wave? It is an electric wave, you see E, and a magnetic wave, and both are perpendicular to each other. You can see that the electric wave is in the XY plane. See the X, Y. So the electric wave is in the XY plane, while the magnetic wave is in the XZ plane. So the electric vector and the magnetic vector are both perpendicular to each other, and both are changing. But notice something, when both reach zero together and both reach maximum together. So although they are in perpendicular planes, they hit the maximums at the same time. And the electric field is given by E naught cosine kx minus omega t plus phi, and the magnetic is given by B naught cosine kx minus omega t plus phi. You may remember that k is the wave number, right? Remember, k is the wave number from waves. So what direction is this electromagnetic wave traveling in? Along which axis? Yes, it's moving along the x-axis. So the electric vector is along the y, the magnetic is along the z, but the wave itself is traveling along the x. So they are all three mutually perpendicular to each other. Very important concept. And we can show that the velocity of electromagnetic waves, c, is 1 by square root mu naught times epsilon naught. Mu naught is the permeability of free space. Epsilon naught is the permittivity of free space. One is the magnetic property, the other is the electric property. These are the values. And when you plug in the values into this formula, you're going to get C is 3 times 10 to the 8 meter per second. Electromagnetic waves can be divided into so many regions based on their wavelength or frequency. But no matter what region we're talking about, all of them have the same speed. So that is 3 times 10 to the 8 meter per second. Here are the regions of the electromagnetic spectrum. Now you can see that the higher frequency is this way, or that's the shorter wavelength, because C is F lambda. When the frequency increases, the wavelength decreases. So the highest frequency is that for gamma rays, then X-rays, frequency decreasing as we go this way, ultraviolet, you got visible, infrared, microwaves, and radio waves. Those are the regions of the electromagnetic spectrum, and you should know how to arrange them in either increasing order of wavelength or decreasing order of wavelength. So know that. And then when we focus on the visible part, you see the visible part is magnified here. It has all the colors from violet to red and everything in between. You have to approximately know their approximate wavelengths. So violet is about 400 nanometers. You see that there? Violet, right there, 400 nanometers. That's violet, because this is ultraviolet. So violet is at 400 and red is at 750. Okay, so know those wavelengths. And also know the properties of electromagnetic waves. Have a basic understanding of the properties of electromagnetic waves, which is very important. Now, like the uses of X-rays, you know that, everybody knows. To find where a fractured bone is, or the presence of a foreign body, like if a child swallows a coin, you can really find where the coin is. X-rays. And so briefly study the uses of all these waves. That's electromagnetic waves. All right, so the next topic is optics, reflection of light. Now, study the properties of reflection where the angle of incidence is equal to the angle of reflection. Know that. And then all these three are in the same plane. The incident ray, the perpendicular, and the reflected ray. They're in the same plane. And using these two laws, we can figure out how a plane mirror produces an image. Right here. It's a plane reflecting surface. Here is the object. To find the image, you need at least two rays. Here is one. Incident ray is reflected that way. The second one at a very small angle, so you got to watch carefully. Here, it's incident perpendicular to the plane mirror, so it comes straight back. Now, these two reflected rays, they're never going to intersect. They're never going to meet each other. That is why we never get a real image for a plane mirror. The image is imaginary. That's why it's called a virtual image. So where is the image? You got to extend the reflected rays backwards, 1 and 2, and they appear. You see the word appear? They appear to be coming from that point. So that is the image of the virtual image of the head of the object. So that's how you get it. And then notice that DO, the object distance, is equal to negative DI. Negative DI because it's backwards. So object distance is negative of image distance. That's here. And then the size of the object and the image are equal. So height of the object is equal to height of the image. Magnification is HI by HO. There's another formula for magnification coming later, which is negative DI by DO. So on both accounts, magnification is 1 because HI is equal to HO and DO is equal to DI. I must say magnification is 1 because the distances are equal and their heights are equal. Okay, that's a plane mirror. Here is a concave mirror. In a concave mirror, we see that if parallel rays fall on the mirror, all of them come to focus. So this is a converging mirror. So if I use the word converging, it's a concave mirror. And since the rays actually meet each other, it's a real focus. It has a real focus. Here is the law of distances for basically a mirror or a lens, the same thing. 1 over DO plus 1 over DI is 1 over F. And here are the formulas for magnification, both the formulas for magnification. What about a convex mirror? Now, look at this diagram. If you look at this, you know that the outside of the sphere is reflecting. That's why it's a convex mirror. Okay, here the inside of the sphere is reflecting. Okay, so here is outside, it's a convex mirror. And when you try to draw and find the image, we only need 2. They have drawn 3. So this is reflected that way, this one is reflected this way, and the third one is reflected this way. And you can see that these 3 rays are diverging. So a convex mirror is a diverging mirror, and it can only produce a virtual image. This is a virtual image. So just like the plane mirror, a convex mirror can only produce a virtual image. But notice, the size of the image is smaller than the size of the object, and the image is upright. That is a convex mirror. On the other hand, we now move to lenses. So be careful. A mirror reflects, but a lens refracts. That means the ray actually goes through the lens. So it's a convex lens now. Could get confusing. A convex lens is like a concave mirror. Yep. It has a real focus and it can produce both real and virtual images. The diagram you see here, is it a real image or a virtual image? Of course it's a real image. How do we know? Because this ray, you see the three refracted rays are actually meeting. And notice that this ray, the yellow one, is not bending. Because if any ray passes through what's called the optic center, the middle of the lens, it won't bend. But the other two bend. See that? So anyways, all three come and meet here. So there's no imagination there. They actually meet. That's why it's a real image. What are the other properties? It's inverted. It's inverted. In fact, let me give you a secret. All real images are inverted. All virtual images are upright. That's a secret. And in this case, the image is magnified. You see that? The image is magnified. It's bigger. The image is at least slightly bigger than the object. And when do you get a real image? If the object is outside the focus, that's when you get the real image. But what happens if you bring the object inside the focus? See, now the object is here. It's inside the focus, much closer to the convex lens. Now you're going to get a virtual image. So a convex lens can produce both real and virtual images depending on the position of the object. And you know the positions now. And again, three rays are drawn. First one, second goes through the optic center, no bending. And then you have the third one. There is a slight bending there, barely noticeable. And you see that they're never going to meet here. So now imagination works. Extend them backwards. And then you see that they appear to be coming from here. So that's why it's a virtual image. Isn't the virtual image upright? Yes, I told you, all virtual images are upright. And in this case, the image is smaller than the object. Concave lens. All right, the concave lens is a diverging lens. It's just like the convex mirror. They are both opposite. That means it can only produce a virtual image. Here is the image produced. So if I give you diagrams, first of all, you should be able to say if it's convex or concave, whether it's a mirror or a lens, whether it's a real image or a virtual image, you should be able to identify the different parts of the diagram. That's very important because that's a question on the exam. Here is the next one. It's called lens maker's equation. So if you want to find the focal length of a lens, and I'm going to just change this formula to make it easier to understand. Lens maker's equation. Let me change this into a plus. It's easier. Both ways will work, but it depends on the explanation. So you want to make a lens. This is a biconvex lens. Both sides are convex. So the radius of curvatures of both sides are taken positive. Convex, positive. So, and n is the refractive index of the material of the lens, right there, assuming that it's kept in air. So for you, you just assume that the lens is always in air, and n would be the refractive index of the material of the lens. So if it's glass, it would be like 1.5, all right? And then using this formula, you can calculate the focal length of the lens. We're going to work out problems later. All right, next topic, refraction. The law of refraction is called Snell's law. And according to Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. n1 is the refractive index of medium 1, which is air in this case, and 2 is the refractive index of medium 2. Theta 1 is the angle of incidence in the first medium. Theta 2 is the angle of refraction in the second medium. So you see that when light travels from one material into another, it bends. The bending could be either towards the perpendicular or away. In this case, it's towards because it's going from a less dense to a more dense medium. So keep that in mind. And the angle is always taken with the perpendicular to the surface. A major mistake that students make. You do not take the angle here. No, you always take the angle between the incident ray and the perpendicular. Keep that in mind. So that's Snell's law. Can easily work this out. Just put the numbers, calculate. If you know what is what, it's easy to calculate it. Now, why does light bend when it moves from one medium into another? It's because of the change in speed of light. So the speed of light in air is not the same as that in water. In fact, the speed in air is maximum. How much is that? 3 times 10 to the 8 meter per second. In water, it's less. And because of the sudden change in speed is why light bends. And you can see that to calculate the speed of light in any medium, you just got to divide 3 times 10 to the 8 by the refractive index of the medium. A very important thing here, which you have to know, is that when light goes from one medium into another, yes, its speed changes, its wavelength changes, but its frequency does not change. Because frequency is what determines color. Do you expect red light in air to become blue when it goes into water? No, never. The color doesn't change, which means the frequency remains constant in every material. It's only the speed and the wavelength that changes. All right, so we talked about that. You got to have a brief idea of polarization of light. Remember that when we talked about electromagnetic waves, we said that there's an electric vector and a magnetic vector. When it comes to polarization, the changes happen only to the electric vector. So we'll only focus on the electric vector. And how is the electric vector? Isn't it confined to one plane? Remember, it was confined to the XY plane. So electric vibrations are just in the XY plane. So in ordinary unpolarized light, you will have, if you have light coming to you, coming towards you, you will have vibrations in all planes because this electric vector, as it moves, is rotating. So it's not just like that, it's also rotating. Remember that. So in unpolarized light, you have all vibrations. You have vibrations in all planes. But when you polarize it, you restrict the vibrations to just one plane. So that's what you mean by polarization of light. And what does that do? Many times it cuts out the glare of light. When you're driving, you do not want the light reflected off the surface of the road to get into your eye because it causes a glare and blinds you. So there you wear sunglasses that are really polarizing glasses. It lets only one vibration to go through. So you're not blind because you still can see, but the glare is cut out because it's the perpendicular vibration, or rather I should say the vibration parallel to the road that causes the glare. So that's cut out and you only get this into your eye. Anyway, so polarization of light. Again, I'm talking about plane polarization because there is circular, elliptical, and so on. Anyway, plane polarization means restricting the vibrations of the electric vector to one plane. That is what you mean by polarized light. There are many laws that you just need to know. Brewster's law, according to which the polarizing angle. What do you mean by polarizing angle? So that theta B is the polarizing angle. It is the angle at which polarization becomes maximum. So if light is reflected at different angles, the polarization changes. Theta B is Brewster angle or polarizing angle. Is given by tan inverse N2 by N1. That's all you need to know. N1, N2 are the refractive indices. So can you find the polarizing angle for glass, assuming it's air and glass? Yes, you can. N1 is that of air is 1 and N2 is for glass, which is 1.5 basically. So if you take tan inverse 1.5 by 1, see it's reversed here, 1.5 by 1, you will get the angle of polarization or the Brewster angle for glass. Interference. Interference is when you have two light rays or two waves rather coming together. Two waves coming together. And they may interfere constructively or destructively. If the two waves are in phase, like you see wave 1, wave 2, they rise and fall together, see, they are absolutely in phase, then you get constructive interference. That means the amplitude becomes double. But if they are completely out of phase, look at this, when this wave 1 reaches positive maximum, wave 2 is hitting the negative maximum. So they're going to cancel out at every point. And what you get is not even a wave. You get a straight line because they are anti-aligned and the amplitude is 0. So there are two types of interference, constructive and destructive. Now we know the difference. And as a consequence of interference, if you have a thin film of oil on the surface of water, and you may have seen this on days when you drive, you have some oil or grease on the road, and when sunlight hits it, it appears brilliantly colored. So that's a thin film of oil. Now, this is a phenomenon that happens with all thin films. For example, a soap bubble. You blow it in sunlight. Oh, it's brilliantly colored. Why? That's a thin film because outside the soap bubble and inside you have air, and separating them you have a thin film of soap. So why do they produce brilliant colors? It's basically because when light is incident on the surface, one part of the light is reflected back up from the top of the film, while another part continues down and then gets reflected from the lower part of the film. So you see, one part is reflected already from here. The second part travels an extra distance down, back up again, and then both of them interfere. So in interference, you have a path difference because the first one came straight up from here. Second one had to go double the thickness of the film. So geometrically, the path difference is 2 times the thickness of the film. You all agree? 2 times the thickness of the film. And if 2 times the thickness of the film happens to be m lambda, then you get constructive interference. That's the condition for constructive interference. What is m? M is either 0, 1, 2, 3, 4, whatever. And lambda is the wavelength of light incident, okay? On the other hand, oh, they have taken the thickness as d. It's okay. On the other hand, if 2 times t or 2 times d, where d is the thickness, is equal to 2m minus 1 lambda by 2, then you get darkness. So that means that wavelength will not be seen. So depending on where you're looking from, certain parts, certain wavelengths cancel out, certain wavelengths are enhanced. So you see some colors and you don't see some others. Anyway, you don't see all the colors because if you see all the colors, then it'll appear white. So since some colors are cancelled out and you see only other colors, it appears brilliantly colored. Did that make any kind of sense? Yeah, that's why soap bubbles in sunlight are brilliantly colored. So white light, as you know, is the combination of all of the colors. You remove certain colors, you're going to see that it's no longer white. That's what I'm talking about. That's interference. Bringing us to the last topic. Remember, this is a review. I'm not teaching you. I'm just focusing on the important parts. Here it's diffraction. What is diffraction? It is the bending of light around the edges of obstacles. So if you have light passing through a slit, as shown here, light passing through a tiny, tiny slit, because the diffraction effect can be seen only if the size of the slit is as small as the wavelength of light, which means it should be very small. Remember, the wavelength of light is in nanometers, like 400 nanometers. So very small slits, it happens. And then it bends. You see that light bends, and the condition for producing darkness here, the angle at which you get a dark fringe or a dark band is sine theta is m lambda by w, where w is the width of the slit. So if you make the slit bigger, then sine theta becomes smaller. So you won't be able to see it. So when you make the width smaller, theta becomes bigger. So it's more resolved, right? You can see the picture here. So where you have darkness, it's destructive interference, and where you have brightness, it's constructive. And here the wavelength used is the wavelength of red. That's why everything is red. So we're talking about a single wavelength here. And this leads us to, what if the slit is not rectangular, but if it's circular? If it's circular, you got to factor in 1.22. See that? That's how the 1.22 came in, because it's a circular aperture. And sine theta r, in this case, where r is resolution. So to be resolved, to see them separate, this is the formula, 1.22 lambda by d. What's d? Two important points here. D is the, in this case, it is the diameter of the circular aperture. So for higher resolution, I hope you're listening, for higher resolution, we want D to be as big as possible. When D, which is in the denominator, is big, then sine theta and theta are small. So what you mean by resolution is the angle must be small. So the aperture must be big. That's why when we use telescopes, we want a bigger diameter for the telescope. We need huge telescopes to see anything close to the star, see? All right, so that's resolution, and that is basically the topics, at least the conceptual parts for exam 3. Now, when it comes to problems, I've already worked out problems in all of these chapters. So would you go back to those YouTube videos where I worked out the problems? I hope you've already done it. Go back there and look at those problems and try to understand them. And on top of that, you've also taken the quizzes, you've done the homework. It should be easy. Focus on the topics that I talked about here, at least conceptually. But remember to work out problems. Look at the YouTube videos where I've solved problems, and it'll all be good. Thank you so much, and I hope you do good on exam 3. We'll see you on the next video. Bye-bye.